All right, in our last video for chapter 6, we are going to prove a very important fact called the theorem of the primitive element. So let me first say what a primitive element is. Suppose you have a field extension. A primitive element is an element theta in L such that L is K adjoin theta. And that's it. So for primitive elements to exist, the extension must be simple, and showing the existence of a primitive element is proving that the extension is simple. All right, so you saw, for example, if you look at the extension root 2 root 3 over q, you can pick theta is root 2 plus root 3 as a primitive element. And that will in fact work, and you proved that, or a version of this, maybe root 5 and root 7, I forget exactly. But you proved, excuse me, a version of that. In your homework, you also looked at root 2, root 3, root 5. Here, if you add them together, this is also a primitive element. And of course, what I mean by this is q adjoin theta is the same as q adjoin root 2, root 3. And of course, what I mean here is that q adjoin theta is the same as q adjoin root 2, root 3, root 5. So although the extension didn't appear to be simple, in fact, it is simple, right? So that's what a primitive element is. Now, our last result here is that basically whenever you have a finite extension, there always exists a primitive element. And these are examples of that happening. So theorem, primitive element theorem, or the theorem of the primitive element sometimes it's called. The theorem is going to be a little bit long, so apologies in advance. But it says, suppose you have a finite extension. Let me be better. Suppose L over K is a finite extension. Then there exists some theta in L such that L is K adjoin theta. So in other words, our slogan is all finite extensions. Of course, we work in C, are simple. That's what this is saying. And when you work in characteristic P, you have to be careful. But for the complex numbers, subfields of the complex numbers, or any characteristic zero field, this is the result holds. So although we work in C, this is not special to C. Any characteristic zero field, the proof will be the same. So proof, well, since L over K is finite, that's the same as finitely generated by algebraic elements. There exists alpha 1 through alpha r in L, such that L is obtained by adjoining alpha 1 through alpha r. Why do this? Well, now we can proceed by induction. So we induct on N. Or on R, sorry, we induct on R. If R equals 1, we're good. This is simple. So alpha 1 will be our primitive element. Otherwise, it suffices to show the case R equals 2 as the general case. So suppose we were looking at we assume the inductive hypothesis, so we have some alpha r up to alpha r plus 1. That, of course, is the same as just adding in alpha 1 through alpha r. And, sorry, I want to do it like this. Let's say alpha 1 up to alpha r minus 1, and then adding in alpha r and alpha r plus 1. And the extension L, which is the big guy, over k adjoint alpha 1 through alpha r minus 1, which is this one, is finite by the Tower law, right? This number divides the degree of L over k. So, so if we can prove it for 2, then we know that by induction it's true for r minus 1. So let me write it down. So if we know for r equals 2, and inductively we would get k alpha 1 through alpha r minus 1 is k theta 1. So k alpha 1 up to alpha r minus 1 is k, and then adding on alpha r plus 1 is like k theta 1 alpha r plus 1. But then we know it for these, we've just added on 2 things to k theta 1. So we can, since we know it for r equals 2, we can write this as theta 1 theta 2. But now it's just 2 things again. We're just adding in 2 generators again, so that's some k theta. So the point is if we can do it when there's just 2 generators that we're adding on, then it must be true in general. All right, so it suffices to prove the case r equals 2, and we're going to do exactly that. So suppose L is obtained by adding in 2 elements, okay? And we're going to not use alpha 1, alpha 2, I'm just going to use alpha and beta to make the notation a little bit simpler, and we're going to set gamma to be alpha plus lambda beta for lambda in k. And we're going to find out which lambdas are going to work. Now think about the primitive elements we did before when we added 2 things. We took the sum of them, right? And here we took the sum of all of them, but we took the sum of them. The sum of them doesn't always work. Sometimes we have to take the first one plus a multiple of the second. And that's all that's happening here. We're taking the first one and then a multiple of the second. Okay? All right, so the goal is we want to determine the acceptable lambdas such that L, which is k adjoint alpha beta, is the same as k adjoint gamma. Okay? Not all lambdas are going to work. For example, if lambda equals 0, then gamma is just alpha, and that's certainly not going to be true in general. So we want to know that the lambdas where this is true. Okay? If we can find 1, then we're done. All right. So let's go and do exactly that. We're going to find an acceptable lambda so that actually beta is in k adjoint gamma. Because if we can get beta in k adjoint gamma, then alpha is just gamma minus a multiple of beta. So that alpha is also in k adjoint gamma, and that will be enough. Okay, great. Now, how do we prove that beta is in k adjoint gamma? Well, it turns out the easiest way is to argue with minimal polynomials. So this is equivalent to showing the minimal polynomial of beta over k adjoint gamma of t is actually degree 1. Because if it's degree 1, then it must look like t minus beta. This is equivalent to saying this polynomial is t minus beta, but the coefficients of this, the minimal polynomial, are always in the field. So beta must be in the field. All right, so that's what we want to do. We want to show the minimal polynomial is degree 1. All right, so let's let m alpha of over k, the base field, be the minimal polynomial of alpha over k, and we're going to factor it over c. So it factors as a product of some roots. This is over c, not over k. Of course, the minimal polynomial over k is irreducible. So this is a factoring over c. And we're going to look at the minimal polynomial of beta, not over k join gamma, but over k. And that's some t sigma minus sigma 1 all the way up to t minus sigma n. And this, of course, is a factoring over c. Okay. All right. So we have these minimal polynomials, and then we look at their factoring. And let's just note something. Since we are subfields of C, the rho I and sigma j are pairwise distinct. Right, we showed that subfields of C are separable, so any irreducible polynomial has distinct roots. So if we look at all of the rho i's, let's use this color. If we look at all the rows, none of them can be equal to each other because we have to have distinct roots. And similarly, none of the sigmas can be equal to each other because we must have distinct roots. Then what we're going to do is we're going to set h of t to be the minimal polynomial of alpha over k, but we're going to compose with gamma minus lambda t. All right, then why do we do that? Well, if we plug in beta into it, we're going to get m alpha k of gamma minus lambda beta. And gamma minus lambda beta is exactly alpha. But this is the minimal polynomial of alpha, so when we plug in alpha, we get 0. So h is a polynomial such that beta is a root, and the minimal polynomial of beta over k is also a polynomial such that beta is a root. And what else? M beta k over the minimal polynomial of beta over k join gamma is a polynomial with beta as a root. All right. This is the smallest polynomial over k join gamma with beta as a root. And so it must divide any other ones that have beta as a root. So in k join gamma, m beta k join gamma of t, that first one that we're trying to show as degree 1, must divide the GCD of h and m beta k. It must do that. Okay. Now, what we're going to show that we show that the GCD of h m beta k has degree at most 1. So it cannot have degree bigger than 1. Okay. And if it has degree at most 1, well, this divides it. This is degree 1. This is degree, therefore degree at most 1, but it has to be at least 1, so therefore this degree 1. So this will finish the proof. All right, so suppose then that the GCD has degree bigger than 1. Then what? Well, then it must be that h and m beta k, the minimal polynomial of beta over k, have a shared 0. And they share a 0, of course, in C. All right, so let's look. The zeros of m beta k are exactly here. They're these sigmas. And you know, there must be a shared 0, which is not beta. Sorry, which is not beta. Right? Because if it's degree 2 or bigger, they share they share beta as a 0, but all the zeros are distinct. So they must share some other one. Let's call it beta prime. But then h of beta prime is m alpha k of gamma minus lambda beta prime. Because that's the definition of h, right? We plug in that expression into m alpha. Since h of beta prime is 0, we must also get 0 here. So this is telling us that gamma minus lambda beta prime is some other 0. Some alpha prime, a 0 of m alpha k. All right, but so if they shared another 0, when we plug that 0 into h, we get that has to correspond to a 0 of the minimal polynomial for alpha. All right, but also gamma is alpha plus lambda beta. So I think we can look at gamma minus lambda beta prime equals alpha prime, and then we can look at gamma minus lambda beta is alpha, and then I think we can subtract them. So if we subtract them, what do we get? We're going to get plus lambda beta minus beta prime, and then we're going to get alpha prime minus alpha, and then the gammas go away. Now beta is not equal to beta prime, because we're assuming more than 2 zeros. So this tells us then that lambda is alpha prime minus alpha over beta minus beta prime. All right, so that was kind of complicated and a lot. So let's just backtrack 1 second here. We saw that the GCD, so what's going on, let's put a thought bubble. The GCD has degree at least 2, so larger than 1, forces lambda to be this combination of the roots. So on the top part, this is roots of m alpha, and on the bottom part, this is roots of m alpha over k, and m beta over k. There are only finitely many such roots of each of them, so there are only finitely many lambdas that would give a GCD of degree bigger than 1. So pick any lambda in k not equal to these expressions, the finitely many difference quotients, to, let's say, any of the, not all the, any of the right? Then gamma is alpha plus lambda beta is primitive, is a primitive element, because the GCD would then be degree less than or equal to 1, but therefore has degree exactly 1 because the minimal polynomial divides it. So it says the minimal polynomial has degree exactly 1, and finally beta is there. So this is kind of complicated proof, and I encourage you to watch this again and go through the book's proof. The book's proof is more or less the same, but I've said things slightly differently. And that completes chapter 6. And of course, the moral here is that finite extensions in characteristic 0 are primitive. Now we see here that if we had finite fields, well, those finitely many bad lambdas could actually just be all the elements of the field. And we see here how we have to be careful when we're working in characteristic P, which we don't. But the proof definitely right here requires that we are in characteristic 0.